Whitehead and Robert Aish of the SmartGeometry group at the A tonight. As you may know, Hugh Whitehead is actually a project director of the specialized modeling group at Foster's and Partners. Lars Hesselgren is the director of research and development at Cohn Patterson Fox in London. Parrish is the director of Arup Sports, and Robert Aish is the director of research at Bentley Systems. All four of them have a background in parametric design as applied in architecture, and their work has actually contributed to some of the most interesting architecture projects in recent times, including the Swiss Re Tower, the GLA building, the Sydney Olympic Stadium, or Waterloo International Station. They're also focusing their development work at the moment on a piece of parametric software that's actually created by Robert Aish at Bentley Systems, and I think Robert is going to show and give us some insights into the potentials of this software in his presentation. In that context, I would also like to take the opportunity to point out that at the moment we are running a SmartGeometry workshop with the MTech program and Diploma Unit 4, and in that context we will have a public presentation of the students' work tomorrow in the soft room at 2 o'clock. So if any of you is interested or will become interested over the run of the presentations, please feel free to join us tomorrow at 2 o'clock in the soft room. I think tonight we will start with a presentation by Parrish. So please join me in welcoming the SmartGeometry group to the AA again. Thank you.
Can I use that one? Yes. I think it might be easier. Oh, good evening, everybody. And thank you very much for joining us for this presentation on SmartGeometry. As Achim has just explained, all the founders of SmartGeometry are actually sitting at this table, and all of us have spent more years than we care to think about working in this field. It dates back to, in my case, meeting these three guys in about 1989, so it really does go back quite a long time. We've all been working in this field, and we had this dream of putting something back into education, and that's really why we're here now. We've held a couple of very successful workshops, one in Cambridge in the UK and the other in Cambridge, Ontario, over the last 2 years. So now it's a pleasure being here and hopefully sharing some of our ideas and enthusiasm for the approach, our approach, which we think is really very much about the future of design. So I'm going to start by telling you a little bit about my personal involvement in this field. It focuses almost entirely on sports architecture, and this is dating back to about the mid-70s, which is a bit frightening, really. It really starts with a personal dream, and I'll come to the conclusion as we get to the end of this. Fresh out of college, I started working on racecourse projects with what was then Lob Architects. And one of the first things I ever came across was a very simple little challenge: how high do you make the steps so everyone can see? Very, very easy thing. So I asked the partner in charge, there was I fresh out of college, and I thought he'll know what the answer is to this. And he said, oh, it's a big stand and you're quite a long way away, so they're about this high. Didn't really seem a very good approach to it, and you can imagine the embarrassment that you'd suffer if you got it wrong, not to mention all the court cases. Fortunately, someone invented a nice programmable calculator, so I programmed out how to do it, and it seemed to work pretty well, I have to say. It actually worked them out for probably the first time, the first time anyone had actually done that particular. Oh, that's very interesting. Complete blank screen. Oh, there we are. Very strange. Anyway, after working it out on this programmable calculator and using it for major buildings, we're talking about seriously big buildings, I then did what most architects do about investing in design and technology and the process of design. I put my head in the sand for the next 25 years. As I say, the calculator had served its purpose, and I updated it all slightly in about 1989 when I went back to Lob Sports Architects, and using MicroStation you could program simple things like how to draw a section of a stand, and it was basically you were putting in the parameters and it would draw them. Very, very straightforward, very, very easy, and at the same time discovered the benefits that working in 3D would create, not only for the process, but in the freedom that it gave one to design very complex forms. Stadium Australia you see here is probably quite unusual. The concept design, which won the first stage of the competition, was done by one person in 10 days, with 3 people to help for the final day. I suspect that won't be repeated for a fair time, that sort of approach. So by the time I was involved as a consultant with Arup for the first time on the City of Manchester Stadium, I still enjoyed the overall process of design. You know, it's a thrilling building type, it's really exciting, plenty of enjoyment there. What isn't so enjoyable, and you'll find this about a lot of what you end up doing when you're working, is that there are a lot of things that are very repetitive, there are a lot of things that you can't do as well as you'd like to do them because you run out of time, and you can't necessarily go backwards and forwards to do them properly. This is the typical project manager's idealized design program. You can see it starts at the beginning and then it progresses steadily to the end. It's a very good system. Every project manager will sign up to that one. Unfortunately, this is how we sometimes seem to end up doing it. And I suspect that other people end up doing the same, and I suppose we're all lucky if we actually get to the end we want to get to. So the challenge is, how do you cut down these iterations? How do you do the whole thing much more effectively? Now, stadium design, like all disciplines nowadays, is becoming very complex, it's very sophisticated, there's a lot that has to be taken into account. So the first task, obviously, is to start analysing those things that are going to give you the biggest benefit if you codify them, write your own software tools. And I've fixed, quite obviously, in the case of stadium design, on the basic geometry of viewing, the way you design a seating tier, the way you make sure you can see over the head in front, the way you make sure people can be close enough to the action. And the rules are actually quite straightforward, and they're easy to understand in this particular case. And using MicroStation and Excel programming both, and they matter to each other, it's a relatively straightforward process to create a bit of code and to create 3D models that are parametric, and if you change the parameters and hit the go button again, it'll change it for you. Very efficient. It enables you to optimize what you're doing, to investigate alternatives in a way that was never possible before. Just to work out a single bowl would probably have taken about a month, just the seating part of the stadium, forget the roof, forget everything else. It probably took about a month before then to do it properly. You're not going to do too many iterations if it takes you that long. We now find that all the work of Arup Sport, this is the current proposal for Lansdowne Road in Dublin, all of it relies really heavily on these parametric design tools, to the point where it would be very difficult to work out how we would do it at all if we didn't have them. This is one example. This is the Beijing Olympic Stadium. It shows, I've pulled the seats out of the 3D model, and just to show what 100,000 seats look like. We had it to this level of detail during the competition phase. So you have the huge benefit of being able to work with accurate information, being able to change it. I'm sure you all know the benefits of parametric design, but the sheer scale of the advantages it gives us are really quite surprising. Now, we progress beyond just doing the parametric design of bowls, because there are many other aspects that respond really well to being able to design the basic principles, codify the principles, and then create tools to build your design. In Beijing, for example, the complex bird nest structure of the roof and the external envelope, the very first stages were not done parametrically, but it was very quickly realized that it was such a difficult task to design this entire complex form without using parametric tools that we just had to go parametric. So we bought CATIA and we started off within Arup Sport a bit from scratch, and now it's all been done that way, and we're just waiting interestedly to see how far it goes through the manufacturing process. We're hoping that the subcontractors will actually have taken it on board and made it work for them as well. And overall, again, huge benefits. So we now have the ability to create complex and accurate designs for much of the building quickly and accurately from day one. This is one of the latest ones we're working on. This is a stadium in the Ukraine for FC Shakhtar, who football fans will probably have seen them playing in the European Championship. It's a major stadium. I think they're hoping to hold the final of the World Cup there, or European Cup there in 2012. have to say I think I've been lucky in the particular field that I've ended up in. Those involved in it will realise quite rapidly that it's not rocket science for most of us. I suspect a couple at this table would have gone on well as rocket scientists, but for the rest of us, it's really fortunate that it isn't. And it's a field where even individuals can make a huge difference. We are not at the stage where you had to be a giant corporation to benefit from this sort of approach. And one individual can actually create tools that enable them to design stadia, as I have, or doesn't matter really what. It could be the design of toilets. It sounds pretty mundane, but if you had to do an awful lot of them, why not work out what the principles are and create software that enables you to design those as well, more efficiently, more easily, and to examine more options and get better optimization. It is, of course, and this is shared with all our businesses nowadays, it's a very competitive world. And so I have to say I dread to think what will happen to firms who don't follow this sort of route, because we found it gives us such a huge competitive advantage. In a few years' time, how will other people compete if they're not doing the same thing? But of course, it's no good just doing it then sitting on your laurels. We've got to constantly progress if we're going to remain successful. What we need to do above all, I think, at this moment in time is we need to extend the proportion of the design that's actually developed parametrically. As soon as we end up having to start making manual changes, we lose a lot of the power of these tools. So for instance, if we make manual changes here and the design has progressed to there and we want to change something, we very possibly have to go back and do all the manual changes again, which means we probably won't do it, and yet we'd have a much better building perhaps if we were able to do so. So our aim now is we're trying to spread the zone over which we can control everything parametrically as widely as possible. Now these athletes at Manchester for the Commonwealth Games, this is, I think it was the opening, they all came with the dream of winning. Now, I too have had a dream, and it's a dream that I've had probably ever since I started this. We're part way to realising it. This is the Shakhtar one, which I was mentioning. I showed you the inside. As part of the process of winning this, we did 4 complete designs in a 1-month period. Totally different, but 4 complete designs. They were rendered, they were animated. Again, very difficult to anticipate how, or to work out how one would be able to do that without this sort of tools. And I think they were undoubtedly fundamental in our success in the project. So we appreciate the benefits. One of the disadvantages that people will put forward to this approach is, well, it'll give people who just press the button once and create a design, that will be the one that's chosen because it's the cheapest way to do it, and therefore we're going to have a lowering of standards. Certainly at this moment in time, we're not seeing that. We're seeing quite the reverse. And I don't see why it should be true in the future either. In the same way that a car manufacturer will not create one design for a car when they're developing something that's very important to the company, I don't think that our clients in the sports venue market are going to necessarily be happy having just one design they take or leave. I think they're going to want to be able to have much more flexibility. This is actually the bowl for the new Allianz Arena in Munich. It's got 66,000 seats, I think it is. This was version 31 of 33. In fact, I think that it was finally 33 that got built. Imagine spending a month on each of those. Well, you wouldn't. It's quite simple. And here we have the reality, a slightly wide view of it. This is nearing completion, all designed parametrically. So my dream is very straightforward. To be able to design a stadium in a day. All elements, all disciplines. And to do another one the next day, until we get the right one. Okay, I'm going to hand over now to Lars Hesselgren, who's going to be talking about the recent SmartGeometry workshop in Arcadia in Canada.
Okay, thank you very much, Jay. I had originally been hoping to talk during this lecture about a current project I'm involved in, but I've been banned from saying anything whatever about it. But in the working with that for the last 6 months, I think I've logged more generative component miles than anybody else in the world, including Robert Aish. So I'm afraid I know the software pretty well. Anyway, just to remind us that, of course, the whole idea of parametric design has been around for an awful long time. This one was done in 1987 when three of us worked at YRM, and I was lucky enough to work with Tony Hunt on the structure of the Waterloo station. And we did what I think was probably one of the first parametric models of a major building at the time. Now, let's talk a bit about what we're doing as a group. We had these people getting together from the 8th or 10th of November last year in Waterloo, and these are people from all sorts of discipline, all sorts of backgrounds, and these are the attendees and tutors. So we had tutors from universities, from MIT, from some of the largest firms of architects in the world. NBBJ, for instance, is, I think, the third largest firm of architects in the world. That's their head of IT and so on. So it's a pretty advanced group of people. They know their way around technology and CAD and so on. And I think they are genuinely interested in this. So the first group we had was in one room, and it was Axel Killian from MIT and Xavier, who's from Foster's. But I thought what I've been doing is I've been slipping in a few of my own slides in the middle of this thing. So this is a slide from MIT workshop where we were exploring the limits to parametrics. And of course, this is the kind of diagrams that you get out. What you're beginning to talk about modeling is you're not just modeling geometry or modeling relationships. And I think you're also modeling intelligence into the relationships, so that when you do things like parametrically change it, the thing will actually talk back to you and do things and change things. And of course, changing things like the numbers of things and so on is very trivial. Now let's have a look at some of the students' approach. This Matthew Jogan from Yale started with a generative component which has got 4 root corners. And it's basically a set of fixed triangles which can deform themselves under a transformation. So you can see here how it deforms itself, and essentially what changes is the shape of the hole in the middle. But all the other components remain the same. And then you take that and you put it onto a design surface, in this case a B-spline surface, which you then dress up with these things. And of course they respond to the underlying geometry. So here you've got a piece of rather interesting geometry, which is essentially made out of 7 triangles which are dressed up. And of course, because we were doing it in a workshop in relation to fabrication, we also fabricated the components at the end of the thing. And of course, the whole idea with parametric design is you swap in any component you feel like. So here he's built a component that is basically a circle, like a trumpet, and the trumpet is oriented normal to the design surface, so that as you design it, and then of course you stretch it out to fill voids, so you get the square thing, the square piece. Judith Kimpian, who I think is actually in the audience here, did a project that I think she said to me that she'd been working on for a long time and obsessed with for a long time. And that is this particular form. What this form does is that as you change parameter, so you distort the form, so you have different types of layered objects which you can change the shape of by changing your parameters. But then, of course, the interesting thing is then to start to take those and array them out so that they obey rules which are given by things like the span and the fact that they each need to nestle into each other. And of course, as you move your B-spline curve around, the whole thing will distort itself and so on. As we start looking at it, she has got an incredibly tidy logic diagram, which I think speaks volumes for her tenacity, because it's quite difficult to get tidy ones. Mine are pretty well impossible to read. Robert is laughing. Yes, he's seen them. And then, of course, we did a physical model of it. Roland Hodson, who might easily also be in the audience, is working on basically equal length meshes, which have, as you distort them, of course, they have a behavior across the surface. So in this instance, we're taking a very simple arc and distorting the equal length mesh across. So it's in effect doing what a piece of chainmail would actually do. And then if you stick it onto a 2D surface, it actually starts to behave itself. And he was then extending it into the 3-dimensional direction. And Roland, we need some better slides of the 3D expansion of this, so if we can have some at some point would be good. In fact, Robert, I think he was in your course, wasn't he? Here at the Aish, so he might have some more stuff. Yeah. Mark Shishi is actually across from Canada because he was one of the students that were over there, and this is what came on the cover. And he did this very elegant form, which is 4 interleaved generative components. So it's a very simple generative component. This is one of the things, getting complexity out of simplicity is really important. So the 3 axes are distorting the generating B-spline curve. It's an ordinary closed B-spline curve, there's nothing fancy about it. But then you nest it into a 4-sided, into 4 groups that are nested together, and then you apply a spiral to that. And having applied the spiral to it, each of the sections, cross-sections, are individually manipulatable so that you can change the form as it runs up the shape. And then, of course, he rendered it, that's a rendering, and physically built a model of it. And that was done in 2.5 days, something like that, and he'd never seen the software before he actually turned up with us. So you can get quite fast forward with this stuff. Now, all of Osterwind is really interesting because that's a different sort of problem. The Hoberman's Ware, if you remember the Atlantic City Winter Olympics, had a backdrop of a 2D Hoberman's Ware, which was collapsed as the backdrop to the stage set. And what it does is it obviously moves, so that this is the mechanism. Now, the interesting thing with parametric design is that something that is moving, which is essentially a mechanism, is trivially easily modeled in a parametric system. So it's a subset of parametric systems. So here you take it and you collapse it inwards. You collapse it inwards again, and then you put it up into 3D, and of course then you get really quite interesting effects in 3D. Suddenly they're beginning to collapse themselves. And of course, in order to get all of this, what you do is, if you find, you then cut it out to make sure that it actually works as a mechanism. Okay, and it just kind of reminded me of a project that we did a while back, which had a opening folding roof, which would have been quite fun to do. I think each one of those fins was going to be about 20 meters big or something. Whether it would have worked or not. The interesting fact is it was actually modeled quite simply as a circular object and then stretched in one dimension to get the thing. This here is a Chinese gentleman who's working in Canada, who was doing a straightforward 3D parametric roof structure, not in itself, I think, in a terribly exciting form, but the nice thing about this sort of thing is that it integrates your manufacturing process, so all your cross-sections are laid out and they are laser cut straight from the 3D model. Change the 3D model, recut the laser cut, re-erect it and reassemble it back to your form. Volker Müller and Rob Woodbury had a separate room, and they talked about architecture and more architectural type approaches. So Greg Lynn architects were there, and they often have this situation of having very curvy walls and objects like that. So what they do is build a system for extracting cross-sectional items so that you have different spanning objects. And this is the kind of situation where KPF has been using the same sort of things. Of course, things like how you triangulate the roof mesh and so on are very interesting and well worth exploring. And of course, you have the ordinary slice and dice thing where you just say, take a form, slice and dice, and there you are. And that's really very trivial and rather boring. I think everybody's been done this slicing and dicing now. Dan Struber was interesting. He had a truss that was deforming itself. And so he built a series of controls. So if you look at those global variables, you will see that those controls control the shape of the trusses at different end of the object, so that you have a form that is gradually distorting and angling itself. His basic idea was that this was going to be used to respond to sunlight and weather conditions. And then, of course, what you do is you just dress it up, render it. Shane Berger, well, this is one of the competition. How am I doing for time? I got 5 minutes, that's good. Shane Berger is one of the competition, and they won the New York Times Metropolitan Interchange, and this was their basic geometry. They came up to the workshop. So we worked with our competitors as well in SmartGeometry Group. We're not exclusive. This looks like GLA building, but as Hugh says, it ain't nothing like it. Its actual fundamental geometry is quite different. This is a series of inclined arcs in space, which are centered on the intersection of 2 arcs in space. and then you triangulate it. It has got a subset of triangulation, which is the triangulation of the glass, and of course you just lay them all out flat and they're all parametrically linked into the model, so when you change the model, all the layout things. But the real reason they were doing this parametric model is they knew everything about the geometry before. That was relatively not trivial, but you could build it as a straightforward CAD model once you decided your 5 parameters. But what was problematic for them is the spiral ramp, is the way the spiral ramp is going to union junction into the space between those two structures. And that's really why they were exploring this. And if we talk about multiple representation, well, this is a slide from a presentation I gave at Bentley Systems about 3 years ago. And this is what I wanted. And this is what Robert Aish has now given us in the technology that we got at the moment. So I think that was a rather successful rant. Robert is really vaguely annoyed with me because I ranted too much at the time. This is a different approach. This is again the slice and dice approach, but this is taking a B-spline surface and cutting it up in terms of a tower. This is kind of 300-400 meter tower that we designed somewhere. Can't remember. Yes, Kuwait, I think it was. Catherine Liapi was very interesting. She has been designing integrity structures, and basically she is working on providing a back-end entry into this. So what she was exploring was the formal methods of doing shapes that could be then dressed up with tensegrity structures. I'm speeding up now because I'm realizing I'm getting up to my end of my time. Judith Lupi from Arup, she has been into planking lines for some considerable time, and Bentley's helped to rewrite her planking routine. So it's now available for inside generative component. So if you start with a double curved surface, and then this is the key item, if you take a plank and you bend it, because it bends unevenly around its 2 axes. So when you put it on a curved surface, it is not going to take up the curvature you expect. It is not just the projection. It is in fact minimizing the normals, I think, kind of. But what it means is that after you built it, you then thicken it up and make it a plank. And you put it in the different directions and you have a look at it, see what it looks like. And then, of course, you manufacture it. The real test, which Robert yet hasn't done, is to just cut them out and just stick them together at the junction points and see that it takes up the proper form. We're pretty confident it will work there. Andrew Kugels, who is also here in the audience from the AA, he was exploring the fact that you can take code, existing code, and plug it into generative components in the back end. So he'd been building this, and I think he told us he went through 4 different softwares, Maya, Rhino, AutoCAD, and so on, in order to produce this. Whereas the nice, big advantage in generative component is all done in one single environment. And of course, changing your parameter to have more honeycombs is not a big thing. Then you extrude the hexagonal grid, and after you've extruded it, you then lay it flat, and you cut it, and after you cut it, you glue it all together, and it will then automatically take up that particular form. Now, this is another slide from my Bentley presentation. And yeah, just a view, sure, all of that's true, and that's what sort of building information management systems do. But I think the real question we've got to ask ourselves is, but what is it a view of? Is it a view of a CAD model, or is it a view of a set of relationships? And I think this is the important thing. This is where I think we're coming back to where parametrics really come in, which is that we're modeling relationships, not geometry. And modeling relationships, not geometry, is a skill that I think is going to need to be taught in schools and with architects. It is a vital thing that we have to do. Okay, just finishing up. What we will do is we'll run another SmartGeometry event in November, and it will be in Cambridge in the UK, probably back to the Miller Centre, and we'll have a conference in London back here. And what we're hoping then is to attract people, programmers and the like, also users of course, who are doing simulation type things, environmental simulation, that can feed back into the design of building systems. Because it's clearly important that performance is one of the issues that will drive form in the future. And we hope that generative components will be a released product at that stage. And this is where I hand over to Robert with a minute to spare.
So I'm going to, and what's interesting about this is the starting point for the Architectural Association workshop we just returned. So this is what the students, the presentation I gave the students for the beginning of the workshop, and then we can look at what they have actually done, basically. So again, we're talking about relationships here. So we're representing the relationships both spatially and geometrically and logically. So for example, I can pick up this point here and move it around, and I can move the planes on this curve. And all the data that I put down there is not just flat data. I'm not just snapping to something. I'm building relationships which are active, and which can be used to kind of explore variation in design. Therefore, it's very important that I establish the relationships that are appropriate. So here I have a base coordinate system creating a set of points into a B-spline curve, and then a set of planes on those curves. So into those planes, I'm going to place some other points and other curves, so that, for example, I can pick up this point and move it on this curve, in this plane, and then pick up the plane and move it down the backbone spline. So I've got complete control over this system. Then I can put a surface through that and do various manipulations, for example. One of the ways we want to explore design is through different paradigms of control. So, for example, it's pretty obvious that we can move something in the actual 3D model. But what I wanted to explore is the idea of creating other kind of control systems, for example, to control the hump of this little saddle surface. So I'm going to create a law curve which goes from, the x-axis goes from 0 to 2, which is the length of this surface, and it goes from +2 to -2, which is like height, if you like. I'm going to put some curves, some points there, draw up just a simple horizontal curve, and then switch over the control of this surface from the points in the three-dimensional model space to the law curve. So it initially starts off flat, and now I can go in here and change the law curve, and that surface can be manipulated. So in this particular case, I've got part of the controls, the height controls, being done by the law curve, but I've got other controls, like the lateral controls, being done in the three-dimensional model. I mean, this is just an example which I've built to show the principles. Of course, the whole idea is that one would adapt this to one's own particular needs. Now I've arrayed a series of points, parametric points, on that surface. So, for example, that command to do that is just one symbolic node on this graph. So, for example, here are these points, and they're defined by a series in U and V. So create points from point 2 to point 8 in steps of 2. And of course it's actually produced all the data that's there. So we're not going around individually putting down points or individually snapping to things. We're creating sets of objects which have relationships to other sets of objects, and where we're manipulating those relationships at a fairly high level. So now I'm going to switch off the surface. Shall we say this was on some roof, and I really wanted to have a beautiful doubly curved B-spline surface as the roof, but client couldn't afford it or something, so I had to rationalize it. So now I'm going to switch off the surface and instead put an array of shapes between those points. They're still being, all those relationships are still maintained. If I move this controlling plane down the curve, if I change the underlying spline, for example, move that in, that is changing the control points, which is changing the surface, and we can see that the surface, for example, is highlighted in grey here, just to show that it's switched off. So the symbolic model is helping us navigate around both the data that is displayed and the data that isn't displayed. But even if the surface isn't displayed, all those relationships are being maintained. So now I can create another model down here, and in that model I can actually unfold those shapes so that as I go back to change this design, change the underlying spline, that is rippling through, changing the surface, changing the points, changing the shapes, and changing the unfold. And of course we could send this to the laser cutter. Green would be the cutting power to cut the material, and red would just be scribing it. And then going back parametrically, we can modify the law curve, and then we can go back and change the interval of the sampling of the surface and get a corresponding refinement of our manufacturing model. Let's go through that. So that just gives you a very quick kind of slice through the whole kind of process. How that we've got all these different representations, conventional three-dimensional representations. This is a sequence of design decisions. It's like a transactional model of design. This is a symbolic model showing the relationships. This is a law curve model controlling those relationships more graphically, and then the unfolded model, which is completely flat, as you can see. All those are interlinked and are active, and are all providing different either controls or feedback about the design process. So that's what we presented to the MTech students. And so I just thought I'd run through just a few slides from one of the projects of one of the students there, which has been pulled out more or less at random, which is about tiling, creating tiles, designing tiles, and then arraying them on a surface. In this case, so that the surface geometry is controlled by the overlap and disposition of the tiles. And what I found interesting about this particular project is the student having seen generative components, that not diving straight in, but very systematically creating some pencil and paper sketches and logic diagrams to explore alternative strategies and dismiss strategies. So you don't spend time going down blind alleys for the software. Very important. And also like establishing the naming convention of what is going to drive it, the length, the width, the depth, the pivot point, the outline, getting a very systematic approach before actually going to the computer. And so this was the model of the single tile that was produced. And obviously we built it up over various transactions. And then we can link this to a set of slider controls. So we've got all these global variables like depths and lengths and outlines and profiles and various other tangency control systems. So essentially with this system, you're designing your own design tool. You're actually designing your interface. It's really magnificent work, considering we gave a tutorial on generative components at the beginning of the week to get to this kind of level of exploration. So it kind of really maybe stimulates some more reflective comments. Of course, design is about intuition and spontaneity, but it's also about logic, and logic really requires some premeditation and some testing, if you like. And particularly what we want to test are things like relationships, both geometric relationships and algebraic relationships. For example, you might have some aspect ratio, or which is going to take one piece of geometry and inform another piece of geometry. And that essentially is leading on to some kind of configuration. And with that configuration, we can wrap that configuration with controls. So you're not actually designing the form directly, you're designing the control system that will create not just one piece of form, but you're exercising it to look at variations in form so that you can discover new possibilities and validate those possibilities against different criteria. And eventually you end up adding not to the relationships more precise data. At the beginning, you're not interested in the precise coordinates of anything. At the end, you can add in the precision. So this sequence is really going from intuition to precision, but it's not a direct path, and it requires a particular kind of thought process. And I'm not going to go through all the kind of different aspects of generative components. This is not just putting pixels on the screen and creating animations. It's looking at things like conditional modeling, multiple representation, how people can extend the system by designing their own components, concepts of replication, just going back how a component can either be or both be an analogy to a discrete physical item that's going to be wheeled onto the building site, or it's a cognitive way of structuring your ideas. The idea of programmatic design, and finally the idea of building a design as a transactional model in which we have this design history which is executable, and we can go back in time, edit that history, and then re-execute it. And therefore that kind of raises a number of issues about what kind of skills, what kind of insights we need. And this is a list that Rob Woodbury, who's professor at Simon Fraser University, came up with. The kinds of issues and the kinds of skills that one has to be wanting to deal with. Issues of composition, issues of geometry, thinking algorithmically and mathematically. And so we did a bit of a test today. Did anybody know what a dot product was and a cross product? Because if you could have, and it's of course vitally important that you have the right design intentions and the right cultural interpretations, but to drive this system does require and stimulates, I think, some more formal thinking about geometry, and that's of course one of the themes that the SmartGeometry group is trying to pursue.
I'm really impressed by the split-second timing.
Well, it's all parametric, isn't it?
I suppose it is.
Put in an interval and.
Okay. So I'm going to talk about Designer as tool builder. These are some examples. I mean, we always look for inspiration, and these are obviously some of the best designs on the planet. They were done by somebody who's been doing it for a very, very long time, even a lot longer than Norman. And one of the things we found over the last few years is that what really helps is to try and build some attitudes of mind. So I've just listed a few that we find helpful. And what attitudes of mind do is they start to shape the way you see things. So one of the first ones is that we always like to try and see geometry as a mechanism. The next one is that we like to see the sketch as a metaphor. And I mean a metaphor for the way you build tools. It goes like this. When you make a sketch, you make a mark, you say what the mark means, then you change the mark, and then you change your mind about what it means. Now, if you keep that in your head when you start to build a tool, and try and build a tool that works like that, it makes a very big difference. So all our tools work the same way. It's very simple. They just say, go out, find all these things, and then do this with them. Going out, finding all these things, that's driving the file scanner. Then do this with them. You have to write or build rules of inference. So this is how you decide what to do and how to do it. And the rules of inference have to link directly to a function library. And a function library takes several years to evolve and build. But it's a very cumulative process. So that's briefly what I mean by sketch as a metaphor, and I think we could talk a lot longer about that one. But it's important also to have an attitude to rationale, and we try to look at rationale as a strategy, because it's very important. At what point in the design process do you introduce rationale so it's helpful to you and not constraining? And because curves is so important to us, we try and look at curves as in their purest representation, which is simply rate of change. So we look for tools which understand rate of change. And we overlay that with rules, but the rules are never about dimensions. They are about proportional relationships. And this is one of the beauties of this kind of approach, because a lot of what we deal with is geometric, and there are lots of systems that apply geometric constraints. And a lot of the other things we deal with, you can write expressions for, so they become algebraic. So the tools of the future will combine the geometric and the algebraic worlds. And so constraint managers are going to become increasingly important, and we're going to look more and more to create an array of solvers which can make this kind of leap. And another thing that helps a lot in our office is to try and view architecture as a team game. There's still room for prima donnas, but as time goes on, we need less of them, but they have to be better. So finally, we put one which is a quote from a mentor that Robert and I share, which is to see computers as amplifiers of the intellect. And that was from Professor Tom Maver of Abacus, Strathclyde. So biomimetics is something that's very fashionable. But of course, a lot of people completely miss the point because they try to mimic biology. And the obvious mistake in this is that we should study the process in order to understand the product. You know, people get seduced by the look of the product and completely miss out on what they could learn from the process. Because all these forms are contextual, adaptive, they learn. And forms like this are very special because they carry on-board performance evaluation. So the form continuously adapts based on the feedback that it receives. So again, another future for us is going to be geometry systems that link to analysis, so we can close this feedback loop. And it's really performance evaluation that leads to this kind of richness of form. And performance evaluation has to be much broader based. It has to cover spatial, sculptural, structural, and increasingly sustainable relationships. This is a setting out drawing. It's a setting out drawing that was used to build Albion Wharf, which stands next to our office. And one of the extraordinary things about it is that it's a setting out drawing that moves. And when we first showed this to the contractor, he said that it's going to cost me a fortune to issue all the brown trousers to the men that are going to try and build this. They found it incredibly frightening that something as precise as setting out data could be part of a mechanism. So that's geometry as a mechanism. Sketch as a metaphor, there are many, many ways of looking at that. Attitudes to rationale. Swiss Re is a good example of a building that was pre-rationalized. All the key ideas were worked out using cardboard and raw intellect. Everybody thinks that Swiss Re would never have been possible without computers. Well, computers were used to great effect in the implementation, not very much in the design. GI is an example of a building that was post-rationalized. Having won the competition, we then had to make it work as a building and also make it deliverable. Increasingly, having learned to do both those things, pre-rationalize and post-rationalize, we found we were building more and more tools which were becoming more and more generic, so they could actually be used earlier and earlier in the process, and also transported from project to project. So this is an early example of a tool that was actually very successful because it enabled us to do things we'd never done before. But this is a single intelligent profile that carries all the information you need to create this form in all its detail. And it's very easy to modify the profile and the rules. And so this way we got very quickly into generative techniques, which was an area that we'd not really explored before. And we found we could explore them also at the detailed level. So this is a little variational template attached to the setting out drawing you were just looking at. And it's going around the roof edge on the canopy and following a set of rules along the lines of go out, find all these things and do this with them. And this is what you end up with. And this whole thing is driven just from a few curves in a setting out drawing, and something that began as a little sketch on an architect's drawing board and then became a little associative parametric profile put the two together, and that's the kind of modeling result that we were able to get. At about the same time, Robert was exploring with a forerunner to generative components. It was called custom objects. He was already looking at different types of expressions and relationships, and he had some fun with the Albion roof because it's a sine wave wrapped around a spiral. But he wanted to be able to do things like have a parameter for the number of humps, or the phase angle of the humps, or the rock angle. So this really got us into a totally new area. And that's what's really encouraging us to try and play architecture as a team game with computers as amplified as the intellect. So I'm going to show you a little bit about a project, West Kowloon in Hong Kong. And just before I start, I'd like to give thanks to the team who produced a lot of the work I can show you. This one, let's fire this one up. West Kowloon in Hong Kong, we won a competition for a master plan, and then the project went away. We thought that's the last of that, and then suddenly it came back in a new version where we had to go into a new competition with a serious proposal of how to build it. So that's what we've been working on for a lot of the past year. It's called the Great Canopy. So how do we actually start this process? We had a conversation with the engineers who said the trouble with architects is that they play around with the shape, and then when they finish, they pass it to us. And when we engineer it and make it work, we always feel if we just had a little bit more curvature in the right places, it would have made a world of difference, because the structure would have worked better, the steel would have been lighter, the spaces would have been more generous, and the form would have been more elegant. So, how do we cut through this loop? So as a result of that discussion, we made this little parametric template. Now, you can see here some control points sitting on an A-frame. And those control points are all you need to produce all the curves that you just saw. But the curves are not created by modifying the control points. The curves are made simply by changing a few parameters. And so at this point, I'd like to go into a GC version of that. Slightly out of sequence, doesn't matter. This one actually is showing GC in action, trying to generate in a controllable fashion the geometry for that canopy. So we place some base points, place some of our magic profiles. Now these are all the same profile, but this one knows how to be an end condition, this one knows how to be a saddle. These are all standard arches, and this one at the tail knows how to be an end condition. So onto those, we start to place surfaces. So you can see here, this row are the front points, this row is the back points, this row are the controllers, and here two surfaces have gone on to create the head. Another three surfaces for the body, another two for the tail. Now, it looks pretty ugly and unformed, but all we have to do is pull out the tangent controllers, and that effectively inflates the head. Do the same for the body, and then the same for the tail. So these are very easy controllers, which are also smoothing out all the edge curves and redistributing the parameterization in the surface. So the next thing is we adjust the control heights, and up she pops. Now, these control heights use the same tangent controllers to smooth out the 3D edge curve. And this is the hardest thing in the world, especially when it's 1.5 kilometers long. And always when you get the long oblique view, you will know if it's not been properly controlled. You'll see every little wrinkle. So then we start to do some head shape tuning. And obviously it's too inflated at the moment, so a couple of parameters correct that. And then we want to have a look at the parameterization in the neck area, where there's something not working. You can see the way the flow lines are getting very contorted going through the neck. So how to fix this? Most parametric systems, they don't have any way of actually controlling parameterization on a surface. So what we're able to do is create that effect. So you see the flow lines instantly smooth out. If you look at it as a surface, that's how it was. That's how it is when it's tuned. And the trick is playing off a combination of two parameters. So I'm just going to show you a little bit about what that system does and what the parameters are. So a standard controller looks just like an arch or a shed. And so when we put the proportional controls on, we can do what the engineers want us to do, which is to make it parabolic, because that's Gaudi's hanging chain, the most efficient structure. But often designers will actually want to go for an arc solution, so that's another parameter. Now the only parameters I've changed doing that have popped up in this window here. I've just put a variable from 0 to 1 in both those cases. Now that is going to an ellipse configuration, the same variable has gone to 2. And suddenly I decided to break some rules, so what I've done here is push a depth factor down to 1. Now all these parameters have a default 0 to 1 range, but 0 underneath it has a hard-coded, sensible, safe default. So that's the magic. So we take behavior which is sensible and useful to us, stick it in as the default, and then put an override control on top of it. So people with no experience of the tool can jump in and start to play from a sensible starting position. And when they go off the rails, all they have to do is put the parameter back to 0 and they're back in familiar territory. So now let's exercise it and go into a little bit of unfamiliar territory. So that's kind of getting interesting, because this tool allows you to talk to any designer in any field, you know, product design. I mean, this is probably talking to Madonna's dress designer. And of course, I'm always told that the problem with this is, you know, if you don't want to get into this kind of references, avoid symmetry. So here we go, asymmetric. Now, the asymmetric is a tilt value of 0.5. What we're putting in now is a skew value of 0.5, which is working in the same direction as the tilt. What we do now is put in some bias, which is also working in the same direction. And then for fun, we can play them against each other. So that is working bias against skew. So these are plain English terms that, you know, as soon as you click it, put a value in, you'll see what it does. And so what I'm trying to get across to you is tool building as an exercise in exploration and communication and discovery. So then, talking to other types of designers, this kind of reminded me of the Bluebird, that wonderful thing used to flash across Coniston Lake. This one is more what I use talking to my boys about waveboards. This one is kind of like a bat wing. If we just go back to the simple shed, all the shapes you've shown have come from the same configuration. There are 4 poles by 5 poles, that's all there is to it. And you don't have to ever worry about parameterization or meshing. Now, it'll also do this, which is puts on an end condition. So you get a dome. And a dome with a perfect parameterization. But if I take I've only got 4 base points, so if I just move them, I've bent it into a kidney bean. If I put a rock percentage in, I've inflated one end. And now if you see that what's happened is I decided to play with the edge condition. So we're starting to actually get curvature into the edge and a much richer form, more shell-like. And this one is really fun. This reminds me of a vacuum cleaner. But you know, the same form has come from the default shed that you just saw. That's the form from underneath. If you look at my parameter list, most of them are still zeros. I put a fairly severe aspect ratio of 6. You know, so this is a thing you can break. The defaults are 0 to 1, but you can exceed it. And this one I really love because I applied a constraint, symmetry constraint. So then, just to see if I could break it, like Alice in Wonderland, I stepped through the mirror and I dragged a point across the symmetry line, and the whole form suddenly inverted. And you're looking at it from underneath here. So this is a single surface that started as a shed or a vault. It's now become a self-intersecting surface, which is complete and continuous, which has all kinds of very interesting spatial, sculptural, structural possibilities. That's another view of it. And yeah, I'm a great believer in a lot of the best things happen by accident. You know, but the point is, this is a very happy accident, which is repeatable. Because it's just stored in a simple parameter set. So any of the things you just seen can be a starting point for a new voyage of exploration. So I think I've said enough, but it just depends if people want to dash to the bar or if they want to see how Kowloon ended up. Because
come on, yeah, come on. I want to see Kowloon.
Do you?
Yeah.
Okay. because these people, I thought I'm going to be let off lightly because they're bound to overrun and then I won't get time to say anything. But it hasn't turned out like that.
See the Kazoo thing.
Okay.
Shoot, man.
So, tool builders. So this is two little tools. You see them sitting down here, and one of them is controlling cross-section, and the other is controlling long section. The cross-section is variational and parametric. The long section is simply law curves. So you can sketch any kind of transition just as you would in an animation interface, and it tells these clever little chaps what to do as they get placed. So they're reading from the curves in the surfaces that we just generated with the surface tool. But they're now placing real components down on there. And they can place whatever you like. So at the moment, they're just placing simple beams. And this is the way we started out. So that system is tracking the center line, putting coordinates out, taking intersections off the edge curves, using that to extract points, which it passes to the clever little tools here. And so it ends up in a surface, which looks pretty good from the top. But the real surprise and delight is like a shell when you turn it over to see what's underneath, because it's generated this wonderful ripple surface. And the ripple surface, was such a surprise and delight. So we charged off with great enthusiasm, exploring this idea of the ripple surface. And it has a very useful construction logic too. So here's some options generated from the ripple surface. We explored changing direction, different ways to get the structure to work more efficiently. This is a ripple surface, which is a throw a stone in a pond version. Different ways of doing that, looking at what happens when the ripples collide, looking what happens when you try and keep the direction going, but you still need to split the span. I mean, these are massive spans. Finally saying, well, what if we don't like the change of direction, have a portion that's bidirectional, so it becomes dimpled like a golf ball. So we had a lot of fun with those, and then suddenly design team decided, no, we're not going there. It was fun while it lasted. So this now looks at ways of getting this roof to work better. And initially, of course, conventional solutions like beams, trusses, tree columns, all the things that you might imagine. And suddenly it was, no, it has to be one thing, one system. So, of course, the only really thing left to us was to try a space frame, which we resisted. What we found is that by doing an unconventional space frame on a diagrid and letting it follow the ripple surface, we got this wonderful basket weave effect, which was quite delightful, but people said, well, you never build that. So we were still looking for a way for making a space frame more readable, because they are such redundant and really confusing and quite ugly things to look at. So this was looking at ways of playing an orthogonal against a lacing against a diagrid. And so we're still just playing these games between two design surfaces that know how to parameterize themselves, and then after that it's just stitching code. It's really like having a giant loom, and you can just put different knitting patterns into it. And these are some of the results. And you can see the beauty of playing orthogonal against diagrid in the same surface is it's not a space frame anymore. It's like intersecting diagonal lattices. But suddenly, they also have a little pyramid that allows the rotation to the orthogonal on the upper surface. And the other real magic was the supporting structure, because this came straight from Norman. The only thing that will look sensible with this structure is if the supports grow down from the roof like stalactites. He said it just has to be the same thing. So this was his sketch, and then this was how to actually make this idea work. And so you have to find a column location, and the code is actually the same as the roof, but it just knows how to reduce and limit itself. So it first of all has to find where's the column location, then it has to find the node distribution, then it has to decide where to set out from. Now you can see these are rules that you can follow wherever you place a column, whatever its geometry is doing, because there are no dimensions, there are no coordinates, it's all proportional. So then we define the curvature of the stalactite. Then we have to drop depth sounding lines down, which we can subdivide so that we can get a system of gradually rotating planes which will define the reduction system. The planes then intersect the original curves and you get two little reduction surfaces. So the original code knows how to play between two surfaces. So now we've got surfaces that know how to reduce. And because they're NURB surfaces, they have perfect parameterization that we can use to place nodes on. So we now have a knitting pattern, if you like, that can feed into the same code and produce these wonderful objects. This is showing the entrance to the Great Canopy, and you actually enter through the dragon's tail, which is quite an amusing idea. And because there's so much curvature, you only need a single support, which is wonderful. And then when it gets into the main body, it actually becomes a diagonal stepping system. And of course, on top of that, you have panelization. So the canopy is a living thing which modifies a very adverse climate. But it doesn't say you're always aware of the climate, so it doesn't seek to exclude it, it just filters it. So this is a whole other story about what the canopy does and how it works. But you know, the ideas are, it's a similar effect to dapple sunlight through a tree. So that's what it looks like. This is what it does. And so anything that happens under that canopy is going through this rich natural experience of the transitions. So Lars said, all I have to do is end up with a fireworks display. So there it is. There's a little postscript to that, because I quite like these kind of metaphor things. And the last one I would add to it is try to see the platform as a playground. And when I say platform, I mean a development platform where we as designers can invite anyone to play. And we hope and believe that GC is going to be that platform. You know, that's why we're here, that's why we're involved with the AA, that's why we're trying to bring together practice, education and research. So, platform as a playground.
First of all, thank you very much.
Discussion?
Yeah, I'm sure there are some questions, and I hope you're happy to answer them. If there are any questions?
Just wondering, has anybody used generative components on a live project yet? It seems to be tested in retrospect. It's actually being built, or is it? You're not allowed to talk about it.
We're designing it for going to planning permission in about April and May, and until then, it's confidential where it is and what it is.
Oh, it's pretty dangerous to be first person in with something.
Basically what we're using it for is setting out geometry. We're not using it to do detailed design. I would say we're probably not as far along as Foster's are in terms of determining the geometry, but it's doing the principal setting out of the geometry, which is important because, like with most complex buildings, complex geometries, you end up with a situation that you change one thing and everything else logically needs to change along with it. And that's the kind of situation where we're using it.
Have you developed a model which architects can play with, as Hugh was talking about, or is it a case of Lars doing it all?
At the moment, it's mostly a case of Lars doing it all, but we are getting to the stage now where we're getting the architects involved in playing with the thing. Certainly the pains of building on a developing software platform shouldn't be underestimated.
What's been the architect's reaction to it?
They love it. Because it means that they can, you know, instead of somebody saying, let's rebuild the model tomorrow because we've changed our mind about something, they can give it to me and I can say, well, you know, this is easy to do with the parametric model the way it's set up. I can generate this change within minutes. Or alternatively, and this is of course the bad bit, is no, this reverses and inverses the logic of everything that we've done to date, and it will take me 2 weeks to rebuild the model from scratch. And those are very difficult things to bring across to people, that building generalized models that take every eventuality into account is very difficult, and it's a real skill. And I must say, I'm always incredibly impressed with Fosters and how they are able to do that.
So there's one little thing I'd like to say. You say danger, and yes, we all know about living with these kind of risks, but it's important to say that it has a very good safety net, because any time that it doesn't suit you, you bail out, because everything you've done is a standard MicroStation element that you can hack with conventional software, convert to DWG, carry on as normal. So, and also the whole idea of the way the platform is structured is that it's based on a migration philosophy. So that users will find they can take something they've sketched in MicroStation, promote it to a GC, explore all the advantages of associativity, and as and when it suits them, bail back out again. So that is a safety net that removes a lot of the danger.
I'm thinking more about if you designed a building and you have a panelization to put onto it, and you think you're advanced enough to write your own panelization code, and then you do it and everything's hunky-dory, and then you get on site and then you find out that there have been some slight errors in your coding. That's the danger of the automation of the detail.
Yes, that just highlights an inability to manage tolerances properly, which is a long, complicated subject. But I think, that's just life. It's nothing to do with software.
Yeah, exactly. I agree. That is, yeah.
And I think that question identifies the difference between a configuration within which you can very easily explore variation, change a parameter, move a slider, everything recomputes, and the need to change that configuration. But at least with the symbolic model, you have a visual representation of what your current logic is, and you can explore, you can explain it to your colleague, okay, we're doing this point, we're making these curves, we're intersecting this, we're creating this surface. You can actually walk through it, and therefore you are in a better position to plan whatever change in configuration you need to make in order to explore a different area of variation.
One of the appealing features with all of these things that I've seen and I've seen before is that you can potentially develop hundreds and hundreds of different variations on the same theme. At the end of the day, does it come down to a pure matter of choice where you plump for one option rather than the thousands of others that you could have generated? Or is there something in the software that you can develop which tells you which is the more efficient structure, the cheaper structure, the easiest one to build, etc., etc.?
I think the whole idea of this is not only can these features represent geometry, but they can represent the measurement of that geometry, and then that can be fed into analysis and performance analysis measures. So you're actually completing the loop, so that, for example, the sliders might be telling you, the gross to net area or something, or the distance to the fire escape. So you're actually, if you have the skill and the inclination, then you can be building in those performance evaluations. So you're not only just making a subjective decision about the geometry, you're actually providing yourself with feedback. I think is that a...
I think that's very fair, but certainly the point is it doesn't take away choice from architects. And also the thing is that it's part of the design process. This is something that design process doesn't change just because you got these tools. People have meetings, people have discussions, people have ideas. Things move forward in the design sense all the time. And what the geometer has to do is to keep up with the design team. Otherwise, he's serving his client, as it were. My client is the design team. But the design team are sometimes irrational. Of course they are. But that's what's delightful about working with design teams, is they are irrational. They do make silly ideas, and sometimes you kind of have to make the tool help them think it through. But that's all it does.
There's one. There is actually a different viewpoint on this. What you're hearing is suggestions for when the designer and the tool builder are different people, And the approach that I would recommend, and one I've followed, is where the designer and tool builder are the same person. And I think what we're going to go through here is the same sort of process that we've had with things like rendering. Rendering, the first time I ever saw it, if you didn't understand where the full stops were and the commas and so on, then you couldn't render anything. And that was the age of the person who had total technical mastery of something that was the real challenge. And then it moves progressively over time as the tools become better to a point where those who are more artistic in nature and are less involved in the ability, or have less ability maybe to build tools, they tend to be the ones that take over the use of those tools. And I think that this type of approach is going to follow a somewhat similar path.
Yeah, I mean, this thing about designer as tool builder, I'm glad you picked up on that, because I suppose people could get the wrong impression, that somebody designs, somebody else builds tools. This is the whole thing about bringing that together. I mean, interestingly enough, the space frame code that you saw was written by an architect.
Very special architect.
A very special architect, yes. But I mean, very encouraging sign. Even in the specialist modelling group, there is only one person who is not an architect, and he's an aeronautical engineer. And in this thing about, we're not looking to technology or software to delegate responsibility, because, it's bound to go wrong, and you can't get away with blaming the computer, garbage in, garbage out.
Yes.
And this thing about, now we're building tools which can generate a lot of options very quickly and very easily. How on earth do we choose between them? Very good question, because you'll use different strategies to make that choice at different stages in the project. And I'd like to make a distinction here between design and construction or implementation. And what happens when you move from design to construction is you start to try to change a process into a procedure. It's very important to have that distinction clear, because design is often described as a process. People don't actually say what they mean by process, but a process is open-ended, indeterminate, whereas a procedure knows where it starts from, and it will always follow the rules, so you can always work out where it's going to end up. And that's what you need when you want to construct something. So as your design settles down, you try to introduce more and more procedural activities. But your design process, which is still loose and fluid, is actually manipulating and steering and helping those procedures to evolve. So when you adopt a generative strategy, you must do it with an attitude of detachment and a self-awareness. You must see yourself in your situation and watch how you're performing, so you've got a management or a strategic view. And I mean, a way to put this really simply, because it's about what Jay was saying, logic and intuition, or rationale and inspiration. Edward de Bono famously described logic as the management of no. And he did this in a book about lateral thinking. It's a very good book, way before computers, but it made a lot of things very clear. But what he never said is, what is the corollary to that statement? And of course, it's obvious, that inspiration is the management of yes. So when you put those side by side, you have left brain activities, logic, no, and you have right brain activities, inspiration, yes, and you have management. So the trick is, how you manage the balance between left and right brain activities. That's the short answer.
And how do you provide an environment in which you can play?
And I think the other one that I think is one of the major reasons why we're here is that we actually expect the next generation of architects to take to these type of tools and this type of approach as a completely natural way in how they work. I think it's the tools are moving in that direction. It's just like rendering. Everybody will do it, and it will be. That's why we're here, because we think that today's architectural students should be learning these techniques as a matter of course, because this is really where I think the future in design lies, which essentially means that Hugh and I are working ourselves out of a job. We're expecting you all to do it, not to have specialists that are like us sitting around doing it for you.
We'll always have a job, because we know what a tangent and a normal is.
Oh, yeah, right.
Somebody told us.
I only found out after a very long time.
Yeah.
You know?
I think maybe Hugh's kidding himself there.
I
think
couldn't
that,
say what a dot product is.
No.
I'd fail on that
In
one.
a few years' time, those will probably be considered trivial in many ways as the tools improve. Once it gets to the point where the designers are genuinely the tool builders and that process is relatively easy, and then if you're not doing that way, it's very difficult to think how people will compete in a marketplace if they cannot do the same sort of work in the same sort of time and to the same sort of quality.
How much mistaking can you do in a day to day?
He does one before breakfast most days.
Oh, put it like this, I've designed significant parts of stadiums sitting in airports, and I've done proposals in 3 days fully rendered for instance, an arena, which is taking quite a lot of detail. It's working out things like concessions and toilet areas and so on, and putting those in, and it's working out all the sight lines, and it's working and adding an envelope, adding a roof structure.
Do you think in 2D at all?
Not really, not very much. I just work in 3D from day one, and I find that that is an easier way to work than to do things in 2D and then transcribe them in some way. Just in the same way, I don't believe in having a secretary who you give a piece of work to and get them to transcribe it. I don't believe in having a designer who then gives it to someone else to do it.
Are there any other questions? No? Okay, then I would like to thank you again. Thank you, Robert, Lars.